So here, this is the step 2 is, so you should show this one. So this implies that omega is scalar. Cn omega j is scalar. And step 3. So we call that covering Vk, which is given by Z0 Zn to Zk Zi. Then the pullback of omega is nothing but I round bar log Zk square summation Tj square. So it is quite easy because, you know, because just the pullback is just you put Zk over Zj over Zk on F. It is exactly the same as this one. So what I mean is F Z equal to log 1 plus Z square. And if we put on Zk over Z, then it becomes a log Zk square. So also the pullback commute with the differential, so it just to come out the in front of this function. So and that, so it remains to show that the only thing we should prove is we need to show that the pullback of omega to uk coincide with phi j pullback omega on uk. If you want, I can write down this computation, but I'll skip this one. Okay. Just the point is, if we even there's a k part here, if we take a Dolbeault differential and the holomorphic differential, then k vanishes. That's the point.
What did you say?
If we so actually this is depends on the variable k, and here this form depends on the variable zj, right? But if we take a Dolbeault operator and the holomorphic differential, then k and j part vanishes. So it coincides with this part. And we call this form a Forbidden study form. So phi k omega defines the Kähler form. And obviously each phi k is holomorphic, right? What I mean is we can pull back the complex structure of Cn to the each open set, and J coincide with the on this intersection, so this defines a Kähler form omega. and we call this Fubini study form. So obviously, as almost of you know, there are so many other construction of Kähler structure on CPN, but this construction is the most easiest way to construct the Kähler form. And actually, this procedure we should do at least one time. This procedure, because actually, for me, there is no chance to Fubini study form explicitly here, so I choose this procedure. So this implies that there's any projective variety is Kähler. So this is almost obvious, because so if we have a Kähler manifold, then any complex manifold of X is again Kähler. Any complex manifold Y with the restriction of Kähler structure is Kähler. Because this is almost obvious. Since Y is complex submanifold, so the restriction of JY is an enormous complex structure on Y, actually integral complex structure on Ty. And if we take any vector V here, then it maps to JV. Then if we put omega to this form, this is obviously non-zero, right? Because this is a Kähler metric. So omega is non-degenerate and obviously closed. So this is again Kähler. And any projective variety is defined by so variety Y is the complex submanifold of CPN for some n. So we are done. It is done. Okay. The last example is the coadjoint orbit. Actually, the previous two examples were in our expectation, because from the motivation and from the definition of a Kähler structure, it is almost clear. But this example is actually not obvious. So to do this, we take a Lie group. And also we used after I will explain about the Hamiltonian action, and after that I will give an example of Hamiltonian action with the coordinate orbit. So we will use this later. And let G is the Lie algebra of G, and G star is dual of G, dual of the Lie algebra. So first we define the co-order joint action here. So let's consider a G action. On itself by conjugation. So which means that G0 acts G by G0 G, G0 inverse. Then, of course, this action fixed the identity. So, which means since every G0 fixes identity, we have the representation of G, which is called the order joint representation. The representation space is the automorphism, the Lie algebra. So which means that G0 maps to DG. Right? So actually DG maps this vector to DTD so where gamma t is the flow, so whose tangent vector at time 0 is x, and so this is the definition of order joint representation. And the coorder joint representation is a dual of this representation. So actually, here is the proposition. Actually, I skipped the proof of this proposition, but it is very easy. The order joint representation actually is a group homomorphism is a Lie algebra homomorphism. I'm sorry, the group homomorphism. Yes. Now we define the coordinate representation. Coordinate representation we denote by AD star is a map from G to the automorphism of the dual of the algebra, which is defined by G maps to some automorphism, which is defined the dual of G inverse. So you know, this one maps G to G, the Lie algebra to Lie algebra, and we take dual, then we get an automorphism from dual to dual. So this is definition of co-adjoint representation. Okay, and the co-adjoint orbit for any element of dual Lie algebra is then nothing but the orbit with respect to co-adjoint action.
Co-adjoint orbit.
Over.
Wow.
AD star G B. And of course this orbit is in the dual of Lie algebra. So we want to prove that we can find the canonical symplectic form on the coordinate orbit. So the claim is there exists a symplectic form omega b sigma omega on the orbit. So actually we construct this form, and this form is called Kirillov constant Sorio form. So actually this coadjoint have contains a lot of important important examples like the flag varieties and of course the CPN, so many interesting manifolds. So and this example is very useful because if we compute something about the symplectic geometry, it is a kind of toy model for computing some invariant. Okay, so to do this, so we put the things. So suppose that G is compact and connected. Then the orbit of beta is diffeomorphic to the homogeneous space G quotient by G beta, and this orbit is some manifold of G star with an embedding. F beta, which maps to so here G beta is the stabilizer of beta. So here the G beta it's a stabilizer. So I briefly sketch up this proof of this proposition. Firstly, we can show that G beta is closed subgroup. Then any closed subgroup on compact connected Lie group is a Lie subgroup. This is called Cartan theorem. GB is G beta is a Lie subgroup. And then it implies that G mod up by G beta is a smooth manifold. Actually, if G beta is normal subgroup, then actually the quotient is again smooth the Lie group. And secondly, let's consider this map from G to the durable Lie algebra, just by which maps to the points where G act on beta. And then you can see that
do you need Cartan's theorem? What is Cartan's theorem?
Any closed subgroup of Lie, compact Lie group is again Lie subgroup.
Oh, that's Cartan's theorem.
Yes.
I thought that this one was the other step.
Yes, it's the Cartan theorem. So this induces a map F beta and actually you can prove that this map is injective immersion. And so any co-ordinate orbit is immerses some manifold of the durable Lie algebra. But if G is non-compact, then we cannot say that it is an embedding. But if G is compact, then the third one is actually F beta is embedding. The reason is that any proper injective immersion is an embedding. So, in particular, when G is compact, then when the domain is compact, then every map is proper. So, in this case, we have the embedding. So, and now we construct the symplectic form on orbit. So here's the step one. To construct the symplectic form on orbit or beta, we need the following three steps. Two steps. So step one is for each beta, which is a point of durable Lie algebra, we define a two-form. Bilinear form. On the tangent space of bilinear form omega beta, which is a bilinear form on the Lie algebra, which is defined by, if we take xy, then it maps to the beta xy. Then the omega beta satisfies the following. It is skew symmetric, obviously, because Lie bracket is skew symmetric. And the second one is corner of omega beta. It is just defined by the vector of the element of Lie algebra, which such that this linear function vanishes. Corner is nothing but Lie algebra of G beta. And third one is third one here. Omega beta is invariant under the omega beta invariant under the co-adjoint action. So which means that invariant. So maybe you know that if the G is other dimensional.
What do you mean by omega beta? It's a co-joint invariant. Omega beta is defined Lie group.
Yes,
but it's not under.
So the co-adjoint invariant means in this sense, omega beta xy and omega on beta there is a co-adjoint action here, G equals, yes, is the same as the so yes,
Something inverse or some.
no, this is true. So I mean, okay, this is something weird, the disjoint invariant. So let's just put this equation. This is the third condition. So before to prove step 1, we proceed to step 2. If we assume everything is turned out to be true, the step 2 is, so now we define for each point of the dual of Lie algebra, we define some bilinear form on the Lie algebra. And step 2, let's define omega on the orbit such that omega r, so I mean gamma, so you know on the orbit, so here I explain the notation of this bracket. So here's the notation. First of all, gamma is a point on the orbit of beta, and x gamma is the fundamental vector field. The bracket x is the fundamental vector field. With respect to the vector x of Lie algebra, and x gamma is just a vector at gamma. So we define this way.
Fundamental vector field of group G, right? Or what do you mean by fundamental vector field? So you have a G still left in what is that?
No. If there is we take an element x, then so okay. Let G act on M. If we take a Lie algebra here, and we pick a point.
You mean this
then
on G's
yes,
top?
yes.
So the
This
fundamental vector field on G's top. The Lie algebra.
Oh yes, on
pure.
G star. P
Sure, yeah.
is the fundamental vector field.
Because G is acting as an adjoint star on
Yes,
top,
yes.
So you have a fundamental vector field.
Yes, over x with respect to adjoint star action, adjoint action. So yeah, actually Actually, I didn't know that I spent a lot of time to explain the basic stuff in the things, so I just sketched the proof of step 1 and so if we define this one, then so we needed to prove that of course omega is symplectic. On the orbit, right? So, so sketch of the proof. The skew symmetric is obvious. For step 1, the skew symmetric is obvious, and let's compute the corner. X is in corner of omega beta if and only if, by definition.
Are you proving this omega
Yes.
beta and also the
Yes. So if we prove all step 1 and step 2, we get a simplex structure on the orbit. So this is just comes from the definition of corner, and it is nothing but beta, the Lie bracket of xy equals to 0 for every y, and this is nothing but the beta dt d0 exponential no, adjoint y is 0. So actually we need some lemma. So I mean the adjoint action G is a map from G to automorphism of Lie algebra. Then if we take a differential at identity, then we have a G to the endomorphism of G. And actually it takes x maps to x dot. So actually this is we can always yeah.
The notation is adjoint G is a map from G to G. You put small adjoints of G, brackets of G.
Yes. Actually, the reason why I use this terminology is I don't want to explain about
Yeah, I think that's it then.
yeah.
That's
Yeah, it is not hard to prove this one. And then it is nothing but the coadjuvant action with respect to minus exponential minus tx beta and y. So because by definition, the autojoint action is defined by taking dual. So if we compute by, then it is nothing but autojoint minus g y. So this comes from the definition of coordinate action. So it becomes 0. So which means that this flow fixed beta. So this implies that x is lying on the g beta. So this is the proof of second statement. And okay. And and I left this an exercise, you know. Actually I have no time to. There's not so much time to prove our handwork, so. Actually, so to prove step 2, so first of all, firstly we should prove the well-definedness of omega. So to do this, if two linear elements represent the same element, then which means that x1 minus x2 on gamma is 0. So which is equivalent to saying that x1 minus x2 fixes gamma, gamma. So which means that x1 minus x2 is in corner of omega gamma by our previous explanation. So actually, so it implies the well-definedness. Actually, no, might as well. And secondly, actually non-degenerate is obvious. Because if we take some non-zero here, then there is, so if we take this one non-zero, then because, which means that x is not in the corner. So the reason is that if x gamma is non-zero, which is equivalent to saying that x is not in the corner of omega gamma, which means that there exists y such that omega gamma xy is non-zero. So omega gamma is non-zero, right?
So omega x gamma is not zero is if and only if x is corner omega y, or what do you mean? The first one.
This one? It's not. Oh, yeah. So because the fundamental vector field it vanishes on gamma, means x fixes gamma, right? So, which means that x is lying on the Lie algebra of the stabilizer. So we need to prove the closeness. To prove the closeness, actually, I just sketched the proof of closeness. Firstly, we should show that omega is invariant under the Coulter detection. So we need to show this one first, and then we take a Lie derivative of omega, which is by Cartan's rule, ix d plus dix omega. This is the, actually we take a fundamental vector field here, then ix d omega plus dix omega must be 0 because omega is invariant under this action. So every directional derivative of omega with respect to fundamental vector field must vanishes. This is actually definition of the AD star invariant. So actually we can prove that this is one form. This is nothing but omega x bracket point. This is one form, and we should prove that actually this is exact form. So I mean is so this is
You're taking Lie derivative with respect to any vector?
Yes, any for any
Lie algebra.
yes, any Lie algebra, and the corresponding fundamental vector field satisfy this property.
And then why this one is
0?
no?
Because it is invariant under this action.
You already assumed that this is
Yes.
invariant.
Yes. This is nothing but the mu x, where mu is a function from orbit as an inclusion. So which means that this one form is exact. So if we take d, then it must be vanishes. And so which implies that
Why is this one form is exact?
so the thing we need to prove that
This
this.
is also another
Yes.
claim.
Yes. Okay, so and the third one is ix d omega is 0 for every x if and only if d omega is 0. The reason is because since the orbit, the tangent space of some point in orbit spanned by this fundamental vector field, G spans the fundamental vector, the T, so x beta, T beta, gamma. So, which means that d omega is 0 for every tangent vector on gamma. So this implies that d omega is 0. So this procedure finished the proof. So we finished our example, and actually I prepared for some real construction for SO3 and UN, but I skipped. I'll explain later if time permits. And okay, here's the final remark, because if the remark is the last thing to tell you about the basic stuff on symplectic geometry. So here's the final one. Just a remark on the almost complex structure. So actually any symplectic manifold is given, then there we can always find the almost complex structure which is compatible with omega. So and also, as in the linear case, the space of our comparable almost complex structure is contractible. Is contractible. So this is the precise, the proof is exactly same as the linear case. So for example, if in the linear case, we take P as an inner product space. Instead of inner product space, we take a space of Riemannian metric here. And this is also convex, because to sum the combination of linear combination is convex. So this is contractible, and we take a map exactly same way as the FG. There is a G, and yeah, we put the tensor. Everything is same. So we conclude that this space is contractible. So which enables us to define the first Chern class. So C1 M omega, which is defined the first Chern class of tangent bundle, the any Chern class Ci J is well defined. So J is any choice of omega comparable almost complex structure. So you can actually, you need to prove that if there is a path, so you should prove that if TMJ, actually it is much more general vector bundle case, we can prove this one. J1 and TMJ2 for two complex vector bundle with the same underlying space, if there is a path JT, then there is an isomorphism from TMJ1 to TMJ2. So let's just think, you can just think of M is a point so that we can regard this one in the vector space case, and then you lift the probe on the general manifold case. Yes, this is the end of this lecture today. So maybe in the next lecture we will deal with the real more mathematical things. So actually this is the end of the basics on symplectic manifold.